Lecture 20, Part 2. So in this part, we will talk about Nash equilibrium, which is arguably one of the most important concepts in game theory. And let me start it with another game called Traveler's Dilemma. So the story is basically we have two identical objects that are lost, and the airline does not know the value of the object. So the airline needs to ask the owners to report their values. However, the owners may lie and report a higher value, so the airline design a game, and the game is the airline will pay the minimum or the lower of the two reported values, and also it will punish the traveler who reported a strictly higher value. So if one traveler report a higher value, then he or she needs to pay the other traveler X dollars, and both of them, by the way, will be paying the minimum of the two reported values. So, for example, if one player reported, say, 100 and the other player reported 99, and then both of them will get $99, but the player or the traveler who reported 100 will get punished by giving X dollars to the other player. So that's the idea here. If they report exactly the same, they will not be punished. They will just get the value they reported. That's the same. Okay, so let's analyze this game the same way as we analyze 2/3 of the average game. And let's start with some guess and say both of the travelers will report something like, say, 100. And the number seems arbitrary, but let's say that the maximum value here, the V here, is just 100. So suppose they both report the highest possible value that the airline can accept. Then suppose I'm player 1, I'm traveler 1, and the other guy is traveler 2. Then should I report 100? If I report 100, I will get 100. But if I'm a bit greedy and I cheated a bit, then I can report 99. Then I'll get 99 plus X. And remember, X is larger than 1, strictly larger than 1. So this thing is strictly larger than 100. However, the other guy will be punished and get 99 minus X. But since I don't care about the other guy, so I'll just prefer 99. But now, even though I don't care about the other guy, I care that the other guy will think the same way as I do and report 99 as well. Then I should probably report 98. Why? Because if I report 99, I will get 99. If I report 98, again, I'll just get 98 plus X. And X is larger than 1. So better than getting 99, actually. So if we continue this process, the other guy will report 98 as well, and they will just go down to 0. And actually, there is a lower bound. Say the lower bound is, sorry, the lower bound is X. And so suppose we cannot report anything that's lower than X, because then there's no way to punish the guy with the lower report. If the other guy is reporting X, would I report X as well? So I cannot report anything lower, so maybe I want to increase it a bit. If I report X, I will just get X. If I report X plus 1, I'm the guy reporting the higher value, so I'll get punished, so I'll get 1. But 1 is strictly less than X, so I prefer X. So given the other guy is reporting X, I'll report X as well. And since the game is symmetric, given I'm reporting X, the other guy will report X as well. So it's kind of a mutual best response. And if I just claim I will report X, and the other player claims that he or she will report X, then we are kind of in agreement, and we call this kind of situation mutual best response. So my action, the action that I claim I'll play, is the best response of the action that you claim you'll play, and the same goes the other way. And in that case, the best response is mutual, and we call these types of action lists Nash Equilibria. So let's go back and let's figure out if there are other pairs that works like this. So we already saw that 100, 100 doesn't work, and 99, 99 doesn't work. Same goes for all the other ones. Maybe let's try something asymmetric. So let's say 98 and maybe 96. So given the other player is playing 96, would I be best responding by picking 98? The answer is no. If I pick 98, I'll get punished. Not only punished, we will both get 96, the lower value, and then I'll get punished x. So if I just report 96, I'll get even higher, 96. Just 96 is strictly better than 96 minus x. If I report 95, I'll get even higher value. So definitely not the best response. So it means already this pair is not a Nash, but let's check the other one as well. So given that I'm reporting 98, would the other player choose 96? And the answer is no. Because if I choose 96, if the other player chooses 96, then he or she will get 96 plus x. But the other player is greedy, and if the report is 97, then 97 plus x, which is strictly larger than 96. So 97 is the best response, not 96. So they are mutually not best responses. So this is not a Nash equilibrium. And you can actually check all possible pairs. And actually the only pair that works like this, like mutual best responses, is x and x. And we're going to call this the Nash equilibrium. And this game has a unique Nash equilibrium. So according to game theorists, we would predict that everyone would do this. Well, realistically, it's obviously inconsistent with experimental observations. Most likely, people will just report truthfully, but in case we don't have a truthful value, they will try to make the best guess instead of just either reporting the highest possible value or the lowest possible value. So there are many reasons why Nash equilibrium, the Nash equilibrium concept is not the best possible concept, but it's still the most popular solution concept for simultaneous move games. And for most of the games, we'll solve it by just figuring out which pair or which list of actions is a Nash equilibrium. So here, let me actually talk about some specific problem with Nash equilibrium. Remember, I said if the other guy is playing the action that he or she claims to play, which is x here, then our x is the best response. However, the other player can lie. So if you have more than two players, the other players may lie and pick something else that's not part of the Nash equilibrium, and then my action will no longer be the best response. But the Nash equilibrium concept does not take that into consideration. So basically, we are always assuming the other player will truthfully play what they claim to play in the equilibrium, and then I just need to check to make sure that I'm also going to play what I claim to play. So it's kind of a stable equilibrium, but it has a strong assumption that the other players will not lie and change their mind. And that would be one problem. And another problem that comes from the same place is that if you have multiple Nash equilibria, then I don't actually know what the other player will play. So for example, suppose you have two Nash equilibria with different actions for the other player, then I have no idea which action I should actually truth. If we don't have a contract, then I still need to guess what the other player is playing. Okay, so these are some of the problems, but again, for the purpose of this course, we don't really care. We just want to use Nash equilibrium as the solution concept of these simultaneous move games. So let's formalize all of these into mathematics. And for a simultaneous move game, which we'll also call normal form games, and actually they are not exactly the same, because normal form games also apply to sequential games. So you can have a normal form of a sequential game. I'll talk about this at the end of this part. But for now, they're basically the same thing. So normal form are the forms that we use to specify simultaneous move games. And here, a state represents just one action from each player. So the state is a list of actions. And so it's slightly different from the sequential game situation. And the costs and rewards are exactly the same. So most of the time, we just call them payoffs, and they are written in a table. So if you have two players, you're actually writing them in a table. If you have more than two players, you're writing them in an array. And if you have two players, there's one row player and there's one column player. And if the game is zero sum, then we can store less information. We can just store the cost of one player, then the other player's cost is just 1 minus that. And usually we'll assume the row player is the max player and the column player is the mean player, but I will specify these on the exams. Okay, so we have talked about best responses like a lot in the previous two parts. So here is the mathematical definition. It's actually not surprising. It's just the definition of best response. So given the other player's choice, I'm picking the best one that maximizes my payoff. So the C here, I'm using the notation C for cost because it's in the search section of the course, but they just represent payoffs. And for the max player, I'm maximizing my payoff, and this best response is the action that maximizes my payoff. And one thing to note is that best response is a function, it's not a value. Because best response of an action is we fix the other player playing that action, then I choose my action. So we need the other guy. We need to fix the other guy's action in order to find the best response. So it's not just one value for no matter what the other guy is doing. And of course, the same thing goes for the mean player. We are minimizing the payoff instead of maximizing. And also the definition of strictly dominated is just as intuitive. One action is strictly dominated if that action is worse in all cases. No matter what the other guy is doing, I always prefer another action compared to this action, then this action is strictly dominated. So let me repeat this. There's a for all here. So no matter what the other player is choosing, I always prefer choosing action S compared to action S prime. Then S prime is strictly dominated by S, or sometimes we say S strictly dominates S prime. And usually we don't really care which action dominates this, we would just say S prime is strictly dominated. Another terminology that may be slightly more confusing is strictly dominant. So strictly dominant is not relative to another action, it's relative to all other actions. So if one action is strictly dominant, it means it strictly dominates all other actions. So basically, it means that action is the best possible action, no matter what the other guy is playing. So basically, if you have a game where all players have strictly dominant actions, then that outcome is first, it's definitely the Nash equilibrium, and also it's definitely the thing that all players will play. And we have a weaker version of this, and it's called weakly dominated. And the only thing we change is changing the strict inequality to weak inequality. And it's not often used because it's not as strong as strictly dominated actions, in the sense that if an action is strictly dominated, then it cannot be a part of the Nash equilibrium. So it cannot be one action in the list of this Nash equilibrium. But if an action is weakly dominated, then it still may be a part of the Nash equilibrium. So weakly dominated is really not that useful in eliminating the actions that will not be played. So we don't often use this concept, but I'm stating it here anyways. And finally, Nash equilibrium. And the definition is actually the same as what we had at the beginning. It's just mutual best responses. But since we have a definition of mutual best responses, now we can state it this way. It's basically a list of actions in which all actions are best responses to each other. That's Nash equilibrium. And when people talk about Nash equilibrium, the first game that comes to their mind is the Prisoner's Dilemma game. So I will assume most of you are familiar with this game, but in any case, I'll repeat the story and also talk about the notations. So we have two players. The two players are two prisoners, and they committed a crime together, but there are no evidence. So if they do not confess, then we're not sure. So they can either confess, which we will use the notation D for some reason, and they can also deny, and we'll use the notation C. So it's kind of flipped, but actually game theorists use the words cooperate and defect, so those are C and D. So it just happens to be the opposite of confess and deny. But in any case, if both of them confess, then if both of them confess, they will both get, say, 1. So it's just a normalizing constant. We just take it as some kind of unit of payoff. So it's not the number of years in prison or something like that. We just say it's 1, so that we can compare this with the other numbers like x and y. And if both of them deny, and as I said, there is no evidence, so they will be put into prison with, say, less years, then they are happier. So x is larger than 1. So basically they prefer both of them denying compared to both of them confessing. So those are the payoffs. And let's compare it to y. So this is the case when the row player confesses and the column player denies. And what will happen is the police will punish the prisoner who lied, and so that prisoner is worse off because 1 is strictly larger than 0. So so that prisoner who lied will serve an even longer sentence compared to, say, in the case when they both confess. So 0 is even less than 1. And y here, so suppose if I'm the only one confessing, then I will serve, say, even a lighter sentence compared to if both of us confess. So y is strictly larger than x. So basically, I prefer to be the only one confessing than to both of us confessing, than to both of us denying, than being the only one who denies the crime. So that's basically an ordering of these payoffs. So the values are not really important. They don't represent anything. They don't represent the number of years in prison or something. They represent an order. So the numbers, the exact numbers, are not that important, and we're representing it this way. Okay, so that's the game, and we want to somehow systematically solve this, and let's do it. X, and this is Y0, and this is 0Y, and this is 1, 1. So using the definition of Nash equilibria, we need to check all possible pairs of actions and check if there are best responses. So for example, let's check whether X and X, or actually we should not specify in this way, we should say C and C, they are mutual best responses. If the other guy is confessing, not confessing, sorry, if the other guy is denying, should I deny as well? No, because if I confess, if I cheat, basically, then, if I confess, then I will get Y, and if I stay denying, I will only get X, and Y is strictly larger than X, so the best response of C is actually D. So C is not a best response. And since the game is symmetric, that other C is not best response. So this is not a Nash equilibrium. Let me actually not cross it out. And we can probably check C and D. So D is the best response to C, but if the other guy is choosing D, D means confess. Would I confess or deny? I would confess as well. So if I choose to deny, which is, I apologize for the notation. If I choose to deny, which is denoted by C, then I will get, what's this? C and D, I'll get 0. And if I choose to confess, then I will get 1. And 1 is strictly larger, so the best response of D is also D. So C is not a best response. So for the same reason, DC is not the best response. So the only one that's possible is D and D. And indeed, we know that the best response of D is D. So we know that this one is the Nash equilibrium. Actually, given this relation, you can see that no matter what the other player is doing, D is always the best response. So D is the dominant strategy and C is the dominated strategy. So the Nash equilibrium is also something called dominant strategy equilibrium. But here we need some way that's faster than just going through all the possible pairs and figuring out which one is a Nash equilibrium. So the way to do that is just highlight the best responses. So fixing the second player playing, the column player playing C, then I'm just going to highlight whichever number is larger. So here, I'm going to highlight Y, and similarly, if the other player is playing D, I'm going to compare 0 and 1. I'm going to highlight 0. So remember, the first number is the row player, and the second number is the column player. So I will not specify this on the exam. You need to know that when we draw a matrix like this, the first number is the row, and the second number is for the column player. And next, we can do the same thing for the column player. So fix the row player is playing C, and I'm comparing these two numbers. I'm going to highlight the larger value, and similarly comparing 0 and 1, I'm going to highlight 1. Whichever cell in the table with both values highlighted, that one is a Nash equilibrium. So if you have a larger game, which we will have a few examples during the Canvas lecture, we'll go through some numerical examples and we'll try this out. it always works and it finds all Nash equilibria of a game. So that's the way that you should do on the exam. Basically, highlight the best responses, and if you have one cell in the table with both actions highlighted, then that cell is a Nash equilibrium. If there's only one, then it's not. 1 or 0, then it's not a Nash equilibrium. Okay, so that's the first game, the most typical example of game theory. And the second one is one that we played last summer on the final exam, and we will do it again this year. So I'll say the final exam, there will be one question exactly like this. You can so the question is basically, you will receive 1 free point, but you can either donate the point or you can keep the point. If you donate the point, then I will actually double your donation and then add that donation back to everyone's final score. So here, the final grade is the number of points you keep, so you can either keep 0 or 1, and plus twice the average donation. So basically, you can choose to donate the point. Everyone can choose to donate the point, and then there are basically 3 possibilities. If everyone is donating, then the average donation will be 1, and I'm doubling it, then you'll get 2 for this question. And if no one is donating, everyone's keeping the point, then everyone's just getting 1. The average donation would be 0, but then you kept 1 point, so it's 1 plus 0. So the worst case for you is actually if you donated point, but everyone else kept the point, then you get 0, and the average is like very close to 0 as well, and twice the average is still close to 0. So you'll get 0. So these are the 3 main cases, and it's possible that a fraction of people would donate and so on. So you need to figure out how many people in the class, for example, are willing to donate and so on. So I will talk more about this, and I will make a Piazza post where you can talk about this among everyone in the class, and I did that last year, and I guess I will not tell you what's the outcome from last year, but I will obviously announce the result after the final exam, so you will know what you get at the end. Okay, so at the end, let's talk about a few properties of Nash equilibria. So first, all of them must be rationalizable. So as I said in the previous part, rationalizable Nash equilibria is a refinement of rationalizable sets. So these things are basically a larger set of solutions, and Nash equilibria is a smaller set. And I mentioned this as well. So a Nash equilibrium cannot contain a strictly dominant action. And the next one is not phrased in a way that I like. Nash equilibrium cannot be found by iterative elimination. So remember, iterative elimination of strictly dominant actions is the way to find the rationalizable set. So this should be written like, so first ID as the S, and I'm using S here because S stands for strategy instead of action. But in any case, this is used to find the set of rationalizable actions. And since all Nash equilibria are rationalizable, so Nash equilibrium, one particular Nash equilibrium would be a part of this, but it cannot be found by using this process. So I do need to make a correction in the version of the slides that I post. So again, we can use iterative elimination of strictly dominant actions to find the set of rationalizable actions. And since the Nash equilibrium is a subset, if there's only one thing, then it must be the Nash equilibrium. But otherwise, it's a larger set than the set of Nash equilibria. And the important thing here is the above statement is not true for weakly dominant actions. So I mentioned this already as well. We may have weakly dominant actions contained in as a part of a Nash equilibrium. And as I promised, we will see more examples like these in the Canvas lectures, and I will also recall some of them before the final exam. So the last thing I want to briefly talk about is the normal form of sequential games. So for the sequential games, we can actually write down all the possible set of strategies, sequential strategies, and just write the payoff in a matrix. But it turns out the solution concept is different. So the solution for the sequential games that we discussed in the previous lecture, that solution I mentioned before is also called subgame perfect equilibrium. It's not Nash equilibrium. So it turns out all those solutions must be a Nash equilibrium, but it's not the other way around. So if you have a Nash equilibrium of the normal form of a sequential game, it may not be a solution. So again, Nash equilibria is a larger set compared to the solution concept for sequential games. I guess it's not very clear here, so I'll actually go through one example in class, converting the sequential game to its normal form, and then solve its Nash equilibria. There are more Nash equilibria than the actual solutions to those sequential games. And actually, I think I posted a video from last year already going through one example of that. So if you want to go through that example and see what I mean by this, you can take a look as well.